Die Altertumswissenschaften haben sich in den letzten Jahren im Zuge der digitalen Transformation entscheidend verändert. Der rasant voranschreitende technologische Fortschritt eröffnet bisher unbekannte Möglichkeiten bei der Erforschung der alten Welt. Neue Instrumente und innovative Methoden durchdringen mittlerweile alle Bereiche der altertumswissenschaftlichen Wissensproduktion, der Wissensverarbeitung und der Wissensvermittlung. Ihr Einsatz reicht von der Entwicklung und dem Ausbau elektronischer Informationssysteme und Datenbanken über die IT-basierte Aufnahme archäologischer Baubestände und deren dreidimensionale Rekonstruktion bis hin zur virtuellen Rekontextualisierung von Objekten durch digitale Anwendungen in Museen. Die altertumswissenschaftliche Forschungslandschaft in Berlin bietet aufgrund ihrer disziplinären und institutionellen Vielfalt bereits ein beeindruckendes Spektrum an Projekten und Initiativen, die unterschiedliche technologische Verfahren erproben, Prototypen entwickeln und verschiedene Szenarien in der virtuellen Realität umsetzen. So entstehen beispielsweise Architekturkomplexe wie das Forum Romanum in seinen unterschiedlichen Bauphasen oder ganze Städte wie das antike Palmyra wieder auf. Oder ägyptische Papyrusrollen lassen sich ohne die Gefahr einer Beschädigung des Originals virtuell entfalten und Keilschrifttafeln geben als hochaufgelöste Digitalisate Aufschluss über die Schreibpraxis im antiken Mesopotamien. Das Nutzungspotenzial digitaler Werkzeuge erstreckt sich damit nicht nur auf die Gewinnung, Archivierung und Auswertung von Forschungsdaten. Nein, digitale Werkzeuge werden darüber hinaus auch eingesetzt, um einen größeren Nutzerinnenkreis, das Altertum in seinen unterschiedlichen Facetten erlebbar, historische Zusammenhänge verstehbar und die Komplexität von Forschungsprozessen nachvollziehbarer zu machen. Heute Abend ist der erste in einer Reihe von Vorträgen, die diese Thematik anhand konkreter Beispiele veranschaulichen. Und es ist mir ein großes Vergnügen und Privileg, den Redner von heute Abend an Sie vorzustellen. Und da er auf Englisch referieren wird, werde ich das auch auf Englisch machen. Professor Bernard Frischer is professor at the School of Informatics and Computing at Indiana University, where he directs the new Virtual Heritage track. He received his BA in Classics from Wesleyan University and his PhD in Classics from the University of Heidelberg in 1975. He understands German quite well, so you're very welcome also to ask questions in German during the discussion. He then spent 2 years in Rome at the American Academy, then moved to the University of California in Los Angeles, where he taught classics, moved on to the University of Virginia, where he directed a digital humanities research center, and in 2013 he joined the University of Indiana, where he now teaches. Virtual heritage, his specialism, is a new field studying ways of applying the new 3D technologies to research and teaching in fields such as anthropology, art, and architectural history. Among the many activities of Professor Frischer, let me just mention a few. He was founding director of the University of California's Cultural Virtual Reality Laboratory, a laboratory which was one of the first in the world to use 3D computer modeling to reconstruct cultural heritage sites. Frischer has overseen many 3D modeling projects, including Rome Reborn, the digital recreation of the entire city of ancient Rome within the Aurelian walls. In 2004, Professor Frischer created the first 3D digital reconstructions of an ancient statue, the lost portrait of the philosopher Epicurus. In 2006, he scanned the first statue in the Vatican museums, the Laocoon statue group. And in 2011, he was one of the first in the world to use photogrammetry to create state models of ancient sculpture and large-scale 3D maps of cultural heritage sites. As a result of this pioneering work, he was invited by the Uffizi Gallery in Florence to digitize in 3D over 1,000 Greek and Roman sculptures in the museum's collections. And in August 2018, the project website, which you can all visit, www.digitalsculpture.org Florence, was released to the public. I've just been looking at this site this afternoon, where it's really wonderful to see all these sculptures from all possible angles, which you can see at no cost. And this brings me to another of his achievements. He founded a new peer-reviewed open access journal published by the Indiana University Library called Studies in Digital Heritage. Among Professor Frischer's numerous awards, fellowships, and prizes is the Pioneer Award of the International Society on Virtual Systems and Multimedia, received in 2005, and the Tartessus Lifetime Achievement Prize from the Spanish Society of Virtual Archaeology, which he received in 2009. Now, from all this, it is clear that a more experienced, distinguished, and appropriate speaker to open our lecture series can hardly be imagined. We are therefore delighted and honored to have Professor Frischer with us today, and we look forward to his presentation on the relationship of the Montecitorio Obelisk and the era Pacis Augustae. Well, please welcome Professor Frischer.
Thank you very much for that very nice and introduction. It is an honor indeed to be invited to speak here in Berlin and at this institution with its great traditions in the field of classical archaeology and classical studies generally. So let me begin by thanking you for giving me this opportunity to present my thoughts about how new technologies can help us to think about old archaeological problems in a new way, using as my case study two of the most impressive monuments left to us from Rome in the time of its first emperor, Augustus. So my case study will use these two monuments left to us from Augustan Rome that are extremely important and well known. The Pacis Augustae, the altar of the Augustan Peace, and what we now call the Montecitorio Obelisk. As you see on the slide, both monuments exist fairly well intact in Rome today. However, unlike the Pantheon or the Colosseum, which have always been above ground and standing in the same place where they stood in antiquity, the two monuments I will be talking about this evening were both buried beneath the ground of medieval and early modern Rome. So to make it possible to see them the way we do in Rome today, they had to be excavated in modern times, removed from their fine spots, restored, and set up on the modern surface. Although they might conceivably have been re-erected where they stood in antiquity, this was not practical. And so they were put where we see them in this slide, several hundred meters from their original locations. This aerial view of our zone of interest today in Rome helps us to appreciate the modern movements of the monuments and also why this very built-up part of Rome could not conceivably have been the scene of traditional archaeological investigation of the monuments, at least for the question that we want to confront today, which is the reason for their spatial and visual relationship. Instead, we have had to use new approaches to take advantage of several new technologies not available to archaeology before 20 or 30 years ago. So let's take a look at the zone in modern Rome where our monuments were found and where they are situated today. And just to orient us, let me point out the Pantheon, which you see indicated on the slide now, the Mausoleum of Augustus. Both of these monuments, by the way, you can see the one is directly aligned to the other, and the diameter of their circles, they're both circular, is exactly the same, and they both were put into Rome, ancient Rome, by the Emperor Augustus. So just to give you two famous landmarks, we can start with those. Now, the Montecitorio obelisk in antiquity was located where you now see indicated on the slide, under a building that has the modern address of Piazza del Parlamento number 3. That's where it was located in antiquity. It was seen there in the 15th century, 16th century, and in the 18th century, it was excavated and removed. And by 1792, it was re-erected with pieces reintegrated and re-erected in front of the Palazzo Montecitorio, which after the Risorgimento became the seat of the Italian Parliament. So that's why we call it the Montecitorio obelisk, because of its current location, which only dates back to 1792. It's actually 200 meters north of where it was in antiquity. What about the Pacis? Well, in antiquity, as you can see, it was fairly close to the obelisk. It was, in fact, 90 meters away to the east, where you see indicated in the aerial photo. But today, it is in a museum 350 meters away to the west on the banks of the Tiber River, right next to the Mausoleum of Augustus. So, if we want to study the spatial and visual relationship of these two monuments to each other, we cannot do it by autopsy, just by going to Rome today and looking at them both with respect to each other. Remember, they were only 90 meters apart in antiquity. Nor can we possibly, if we want to find out more about their ancient context, excavate that area in the modern city, which you have seen is completely built up by buildings dating from the late Middle Ages to the 19th century. Well, when we see the obelisk and the Pacis today in the Eternal City, we are, I think, all of us, overcome with a certain feeling of awe. But as we will see this evening, we should not confuse our modern reaction to these monuments with a very different, and I dare say much greater impact that they must have had on the ancient viewer. I say this for two reasons. First, because however well preserved they are, they have suffered significant damage and degradation. I need only note the complete loss of the polychromy decorating the altar. Second, and more importantly, they have been torn from their original urban context, and so we do not see them together and experience how they interact with each other and, as we will see, with the sun as it moves overhead. And the sun, for its part, is not moving overhead in the exact same way that it did 2,000 years ago. Aristotle famously insisted that the whole is greater than the sum of the parts, and such is certainly the case with our two monuments. When we consider them as two parts of a greater whole in their original Augustan context, we can understand them far better than is possible today if we just see them when we visit Rome. Let me explain. These monuments were located in the part of the ancient city we call the northern Campus Martius, or the Field of Mars, the Roman war god. It had this name because in the Republican city, the army mustered here for its training exercises. Prior to Augustus, the Campus Martius was largely undeveloped and a rather scruffy, unimpressive tract of land. And this is owing to the fact that the nearby Tiber River not infrequently overflooded its banks, covering this low-lying land with water and alluvial silt. With Augustus's assumption of total, undisputed power in the state after the defeat of Antony and Cleopatra in 30 BC, work was started to transform the area into beautiful gardens punctuated by monuments celebrating the new regime, like the Mausoleum of Augustus and the Pantheon. This great public park was praised for its beauty by the Greek geographer Strabo, who visited Augustan Rome and whose geographical work is preserved. The monuments in the park began to be built in the 20s BC and included the Pantheon at the south, the Mausoleum of Augustus to the north, and Augustus next restored the Via Flaminia, which forms the area's eastern limit. By the period of 13 to 9 BC, Augustus got round to adding his finishing touches to the urban design. This was when the Areopagus was built to celebrate the emperor's victorious return to Rome on the 4th of July of 13 BC. It was completed in 9 BC and dedicated on the 31st of that year, which happened to coincide with the 50th birthday of Augustus's wife, Livia. Meanwhile, an enormous monolithic obelisk was being transported to Rome, all the way from Heliopolis in Egypt, near modern Cairo. It was erected in the same part of Rome in 9 BC, according to its still extant dedicatory inscription that we'll see later on in my talk. Its new location was just 90 meters west of the Areopagus, and there was nothing in between them and nothing in the general area except this beautiful public park. The obelisk and altar are not only of intrinsic interest for us as two individual witnesses of the art and culture of Augustan Rome, but as a pair, they also possessed added meaning for the people fortunate enough to see them in ancient Rome. That they should be considered a pair is clear from the fact that, as we have noted, they date to the exact same period, and also from the way Augustus and his designers arranged the monuments on the ground. As you can tell, if you look at the north arrow in this slide, the altar is rotated off the cardinal points by 18 degrees to the north to be parallel to the nearby Via Flaminia. This is not surprising. You would see the altar as you were walking down the Via Flaminia, and so it's not surprising that it was made to be parallel to the Via Flaminia, which itself is rotated 19 degrees west of north. It is, however, surprising that the base of the obelisk was also rotated by just about as much, 15 degrees west of north. Moreover, as we will see, the obelisk rotation is strange because the obelisk served a second purpose. So not only as one purpose to be visually linked to the altar, but a second purpose to be the support for a large sphere, a globe, whose shadow was cast onto an adjacent bronze meridian line on a pavement running off the base of the obelisk due north. And thanks to the great work of Professor Edmund Buchner, a 5.5 meter section of the meridian was brought to light in 1980. And that's me, not Professor Buchner, in case you're wondering. Its location is indicated in red on the plan. The rest of the meridian, indicated in yellow, still lies buried 7 to 8 meters beneath the modern buildings along the Via di Campo Marzio. We know a lot about the meridian, even though 60 meters of its 67 meters or so of length are still buried below the modern surface. Just to drive home the point that the two monuments constituted a pair, the obelisk was sited on an extension of the line of axial symmetry of the altar, which you can also see in the slide. This means that anyone standing on that line to the east of the altar or to the west of the obelisk would have seen the two monuments intervisibly, in alignment. And that alignment even extended to their rotation off the cardinal points. They're parallel to each other. On this slide, you see an example of what someone standing east of the Areopagus would have seen when she looked to the west. So with this background in mind, you are prepared to understand scholars' traditional questions about the Areopagus and the Montecitorio, and scholars traditionally have not doubted that they are a pair. that was first observed by an Italian scholar in the 1930s, and I don't think anyone since has denied that they are visually linked, just as I have been arguing, and for the reasons I have been arguing. Of course, scholars have many questions about our monuments. Fortunately, Professor Lothar Hasselberger's recently published volume, with his report giving the status questionis, goes over all the questions currently under debate. We can boil them down into two big issues. First, what was the design of the timekeeping device of which the obelisk and the meridian were a part? Secondly, what is the reason for the visual alignment between the Pacis and the obelisk? My goal this evening is to show you that we can use new technologies next to older methods to make progress in answering both questions. So let's start with the first question, namely the design of the timekeeping device. It was described by Pliny the Elder in a very famous passage in Book 36 of his Natural History as follows. The Emperor Augustus used the obelisk in the Campus Martius to construct a marvelous sundial on which the shadow cast by the obelisk indicates the length of both days and nights as marked out on the stone pavement built to measure it. It is altogether an object worthy of study, a creation of the mathematician Novius Facundus. He added a gold ball to the top of the obelisk, which gathered a clear shadow around it. These measurements, however, have been inaccurate for about 30 years now. For centuries, scholars have tried to interpret the meaning of Pliny's words, which can be taken in one of two ways. The first theory is that the timekeeping device was a large horizontal sundial as big as 160 meters wide by 70 meters long. The sundial would have had the lines of all or most of the hours of daylight. The second theory is that the device was simply a meridian, that is, a north-south line for the 6th or noon hour every day. If this is correct, the dimensions of the device would have been much smaller, perhaps only 10 to 15 meters in width by 70 meters in length. As you see on this slide, the horizontal sundial theory goes back to Athanasius Kircher in the 17th century. It was revived by Rodolfo Lanciani, who put Kircher's butterfly design of the sundial onto his still much used Forma Urbis Romae, which gives us the ancient ruins superimposed over a map of the modern streets. After a lapse of some decades, the theory was revived by German historian Edmund Buchner in an influential article published in 1976. In that article, and in other works subsequently published down to the year 2000, Buchner repeatedly called the monument the biggest sundial in human history. In the slide, you have been seeing Buchner's illustration of how he imagined the horizontal sundial to have looked. Its dimensions, according to Buchner, would have been about 70 by 160 meters. The second theory is that the timekeeping device was not a big sundial, but something more restricted, a meridian with just the noon hour. This idea can be traced to the Renaissance. In 1750, it was argued at great length by a number of notable scholars, including Ludovico Antonio Muratori and Leonhard Euler, in a collection of essays on the problem published by Angelo Maria Bandini. This work is still often cited and is quite valuable despite its age. More recently, the meridian theory has been defended by engineer-gnomenologist Paolo Alberi Albert. And by the way, a gnomenologist is someone who designs sundials and related devices, which engineer Alberi Albert does for a living. In this slide, you see his drawing of how he imagines the monument to have appeared. And let me take this opportunity to thank engineer Alberi Albert for all the help he's given our project over the last 10 years. He's been most generous and kind. As Hasselberger's review article made clear in 2014, Buchner's theory has dominated thinking about the problem during the past 50 years. So before showing you how my team has been working off and on during the past 3 years to determine which theory is correct, let me give you a bit more background about Professor Buchner's theory. The theory had 3 parts: the setup of the monuments, that is exactly where they were sited in the ancient city. As I've mentioned, Buchner speculated that there was an enormous pavement, 70 meters north-south by 160 meters east-west, on which were inscribed the lines of a horizontal sundial, giving us the 2nd through 10th hours of the day. Buchner didn't think there was enough room for all 12 hours because the 11th and 12th hour would have oversprung the Via Flaminia over to the east of the Pacis. He thought that the sphere we know from Pliny that stood atop the obelisk was the gnomon or pointer for the sundial. That is, its shadow would have fallen on a line to give you the day and the hour of the day. The second element of Buchner's theory concerns the environmental effect caused by this setup. Buchner thought that the effect concerned the shadow cast by the obelisk on Augustus's birthday, September 23rd. In particular, he speculated that the shadow went down the equinoctial line right into the middle of the Pacis. And at this point, it will be useful to look at an illustration of the effect that Buchner must have had in mind. He never actually illustrated it per se. But in this slide, you can see the obelisk shadow cast into the middle of the altar, carrying out what Buchner only described in words. But note, by the way, that the date that we are illustrating here is not September 23rd, Augustus's birthday, but the 28th of September. And so I don't mean to imply that Buchner's theory is correct, and as we will see, it is, alas, not correct. Finally, the third element was the message implicitly transmitted by this environmental effect. Buchner thought it was that Augustus was born to bring peace, or natus ad pacem, was the Latin motto that Buchner coined to capture this idea. To his great credit, Buchner not only revived Kircher's theory of the horizontal sundial, but 4 years later, in 1980, he also tested his theory by undertaking a small excavation in the basement of a building where he thought he could find a small section of the pavement with that equinoctial line so critical for his theory inscribed in bronze. The building in question is an apartment complex at number 48, Via di Campo Marzio. Buchner's team worked here in 1980 and made a wonderful discovery. Not the equinoctial line they were looking for, which would run east-west, as you've seen, but instead a 5.5 meter long section of the meridian, which ran and still runs underground, north-south. You see what Buchner found in this slide on the screen. Now, this discovery was spectacular and brought to Professor Buchner quite a bit of well-deserved attention in the world press. However, there was a little problem. The level at which the meridian line was found is 1.5 meters higher than Buchner had predicted in 1976. And as you can see in this slide, the line itself is located over 4 meters farther to the west than had been predicted and 3 meters farther to the south. Buchner's expected line is at D on the plan. What he actually found is at B, 4 meters to the west and 3 to the south. So Professor Buchner revised his original theory such that the entire horizontal sundial was supposedly restored at a higher level decades after the death of Augustus during the Flavian period, founded by its first emperor Vespasian in 69 AD. Everything was also moved 4 meters to the west and 3 meters to the south. You will remember that Pliny wrote that the timekeeping device was no longer rendering accurate time when he was writing, and he, we know, was writing in the 70s AD. So according to Professor Buchner, the restoration would have taken place before Vespasian's death in 79 AD. And he speculated that what he found was that Vespasianic version of the monument. So according to Professor Buchner, the timekeeping device was not only a large horizontal sundial, the biggest in human history, but it also had 2 distinct phases at 2 different levels with the lines inscribed on this big pavement in slightly different places. An Augustan phase at 9.2 meters above sea level and a Vespasianic phase at 10.8. From the start, Buchner's theory encountered fierce opposition. Anyone here in the field will certainly attest to that. We don't have to go into that opposition today, but let it suffice to say that one of the critics' main arguments was that no ancient writer reports a second phase of the monument. Our team's work the past 3 years has tackled both elements of Buchner's theory. First, that there were two phases, Augustan and Vespasianic, and second, that the timekeeping device was the biggest sundial in human history, that it was a horizontal sundial as first proposed by Athanasius Kircher in the 17th century. Our goal was to move the question beyond merely nitpicking the logic of Professor Buchner and his assumptions by bringing to light new hard facts. The first hard fact that we were able to discover concerned Buchner's theory of the two phases. To test the validity of that, in July of 2016, we simply made a geological coring through the pavement of the meridian that Buchner had discovered. And I hasten to add that we, of course, had the permission of the archaeological superintendency and the owner of the building, this private building, to drill this hole. And we could do so because the place where we drilled, indicated by the red arrow, was, as you can see, already damaged. The surface was gone already. So by drilling a hole there, we weren't really damaging a precious ancient monument. Our reason for coring here should be clear. Buchner's two-phase theory required that there ought to have been an Augustan pavement, or at least its preparatory layer if the pavers were robbed out and reused at the later Vespasianic level, which Buchner also proposed. But the mortar bedding would have remained at the Augustan level, 9.2 meters above sea level. So in July of 2016, we drilled a core 1.8 meters deep through the pavement. As the report on the screen shows you, all that our geologist Stefano Flores found in the core were alluvial layers. Alluvial deposits are created by the flooding of rivers, in this case, the nearby Tiber. They are completely natural, and the layers found by Flores could have resulted from many centuries or even millennia of flooding in this area. And that means that there was no man-made feature at the level of the pavement hypothesized by Buchner to be Augustan. And the inevitable conclusion is that the timekeeping device had just one phase, the Augustan phase. So the Augustan phase must have been at 10.8 meters above sea level, not at 9.2 meters, as Professor Buchner had speculated, meaning that all those lines were not moved. Everything that Buchner found is just where Augustus left it. Now, what about the overall design of the monument? Was it simply a meridian, the noon hour, of which Professor Buchner found a part? Or was it, as he thought, an enormous horizontal sundial with that big travertine pavement, 160 meters east-west, 70 meters north-south, giving most of the hours of the day? To address this question in the most efficient and economical way, our team used a different approach, remote sensing. Remote sensing in this context means a method whereby we obtain information about subsurface features not physically by digging or coring, but by transmitting electromagnetic signals into the earth. This work was undertaken in July 2018 by our team member, engineer Gianfranco Morelli, and I'm tonight giving you the first report about what engineer Morelli found. And you might recognize his name from press coverage last year of his work searching for hidden chambers in the tomb of King Tutankhamun. And Morelli found out that there were no such hidden chambers as had been speculated. This evening I will be giving, as I said, the first public presentation of his results. Morelli used two approaches to do this remote sensing: ground-penetrating radar, or GPR, ground-penetrating radar, and electrical resistivity tomography, or ERT. We were able to get permission from many of the owners of property in the area to apply GPR and ERT in their basements and courtyards, and we are grateful to all of them for giving us access. This included even the Church of San Lorenzo in Lucina, and, even harder to obtain access to, the big police station next door to the church, covering a large area in the north-central zone of Buchner's hypothesized sundial. And we also applied GPR in the streets in the area, as you will see. Well, in this slide, you've been seeing some action shots of the work in progress In this slide, you see the area where in 1976, Professor Buchner speculated that the horizontal sundial stood at 9.2 meters above sea level in the Augustan phase. In this slide, you see where Morelli and his team did their GPR and ERT work. In this slide, I've created a short video in which you see Morelli's map superimposed over Professor Buchner's hypothetical plan of the horizontal sundial. As you see, at our request, the area studied by Morelli largely overlaps with where Buchner's theory would lead us to expect to find evidence of a pavement or its preparatory layer, if there really was a large horizontal sundial. Before I show you the results, let me say a couple of words about GPR and ERT. Perhaps not everyone present tonight would agree in calling these new technologies in archaeology in the strict sense of the term. They have been used with increasing frequency for at least the past 20 years. I myself used them in the 1990s when I excavated the villa attributed to the poet Horace at a town outside of Rome called Licenza. Whether you would characterize GPR and ERT as properly new or fairly new technologies in our field, we can all agree, I think, that they are certainly newly applied to the problem at hand. Nobody has ever applied them in this part of Rome to address the problem that interests us. As the name implies, GPR entails transmitting a radar pulse from a device on the surface of the Earth to visualize non-invasively, without any digging or any damage, to visualize what lies below. The devices look remarkably like a vacuum cleaner or perhaps a lawnmower, which you might have around your house. The device has wheels, and you push it in straight lines called transects across the surface. The device utilizes the microwave band of the radio spectrum. When the radar beam of the GPR device strikes the subsurface, it gives back a reflection off the boundary between objects with different material characteristics. These reflections are recorded on a computer attached to the device, and they are outputted as a graph, such as the two you are seeing in this slide on the lower right. Of the two, the lower one, labeled L3, is quite interesting. We'll come back to it in a moment, so let me make clear, which I've already done, which of the two graphs I'm referring to. Now, let's apply these generalities to our case study. If Professor Buchner's theory is correct, then we should expect to find the travertine pavement, or at least the preparatory mortar layer, reflected back to us by the GPR all over the zone. But what did the GPR reveal? First, we found absolutely nothing anywhere in the area at Buchner's hypothesized Augustan level of 9.2 meters above sea level, his Augustan phase. Everything at this level appears to be just the natural alluvial soil, just as we had found in July of 2016 when we cored through the damaged section of the meridian. The conclusion we reached was thus that Buchner was wrong about two phases. As our coring through Buchner's meridian had already suggested, there was just one phase of the monument. It must be Augustan in date, and it stood at 10.8 meters above sea level. Well, what about that level? Was there a big travertine pavement, 160 meters wide from east to west, as Buchner's theory called for? In the event, we found nothing at that level as we went 20 to 80 meters east and west of the meridian, going from the Via di Campo Marzio, along which the meridian was found, as far west as the Via della Lupa, or as far east as the Via del Giardino Teodoli, and any place in between. We also worked in between, as you can see from those red and blue and green lines. So from 20 meters from the meridian to the 80 meters east and west, so across the whole 160 meters east-west of Professor Buchner's hypothesized pavement, we found nothing. So our conclusion is that the monument was not a big horizontal sundial, but just a meridian giving the noon hour. One of our GPR transects gave us a strong clue about the width, about the design of this meridian and its travertine pavement. I again draw your attention to the transect we called L3. You see the graph of the results indicated on the screen. As the map shows, L3 corresponds to that green line that started west of the meridian and followed the Vicolo della Torretta across the Via di Campo Marzio right into the entrance and courtyard of a building at number 46 Via di Campo Marzio. The building is of great interest because it is the next palace north of the site at number 48, where Professor Buchner found the section of the meridian pavement. Number 46 has never been studied, and we are grateful to the owners for letting us investigate it. Here is an X where Buchner's meridian presumably is still buried below the building. The GPR transect L3 shows strong evidence that the meridian did continue here, as was only to be expected. What makes this graph, though, particularly interesting is that the data of L3 also indicate that the pavement flanking the meridian line ran for approximately 7 to 8 meters to the east and the west. Now I will click and put a red box around the relevant data on the graph, showing what could very well be the profile of the meridian flanking the pavement. Just to be clear, I'm talking about this data, which perhaps give us the actual meridian pavement. You can see that it's symmetrical with this dotted line here, which is the position of the meridian as projected from number 48, just to the south. So to summarize, our new coring and remote sensing lead us to view the timekeeping device as having had just one phase, Augustan in date, and as having had a design that was a meridian with a bronze line just for the 6th hour, set in the middle of a travertine pavement, 14 to 16 meters in width. In the slide, you see my laboratory's restoration model of our findings. Needless to say, without the use of the new technology of remote sensing, we could never have gathered all these new data about the ancient level in such a built-up area as we find in modern Rome, where large-scale excavation is simply inconceivable. With this background in mind, we can move on to the second question. What is the reason for the alignment between the Ara Pacis and the Montecitorio obelisk? Here, too, technology can help us to bring new facts to light on the basis of which we can hazard a new interpretation. And this time, I think it is fair to say, without any doubt, that the technology is really quite new, and I will be showing you something brand new, just has existed for the last 5 days tonight. And it is the new computational technologies that will help us, in particular, a computer simulation of the ancient Roman environment. Of course, we had to use a computer simulation because, as you have seen, the monuments are no longer in their original locations. The city sits 7 to 8 meters higher above sea level, and just to add icing to the cake, the sun's apparent path through the sky has changed quite a bit since the monuments were completed way back in 9 BCE. Now, although it is still relatively new to use computer simulation of any kind for tackling any problem in the field of archaeology, it is worth pointing out before we do so that the use of such simulations is quite common across the sciences, from physics to biology to economics. Modeling has been for decades the name of the game. 3 general uses of computer simulations have been identified by philosophers of science, for whom this is a major topic: the validity, the epistemic value of computer simulations across all of the sciences. And so in this vast literature can be brought to bear to help us in our own methodology in applying computer simulations to our problem in Rome. And 3 general uses have been identified: communicating existing knowledge to others, producing new knowledge from data we already possess, and predicting, or in the case of historical study, what they call retrodicting, data that we lack. It is this last use of retrodiction that I think is the most immediately relevant for the discipline of archaeology, which you may have noticed is, as you will have noted, is not one of the sciences that philosophers of science have studied with regard to computer simulations, because they have been, in our field, so rare. And my main goal today is to suggest that the time has come when our field can begin to catch up with the other sciences. Of course, in archaeology, simulations per se are not new. You have only to think of the many physical models archaeologists have created to illustrate how they imagine an ancient work of art or architecture may have appeared when new. The physical models have served the same purposes as those identified for the new computer simulations. For example, since the 19th century, casts have been used to show different hypotheses of restoration of sculpture. Here you see Georg Treu's use of a cast to experimentally restore the lost polychromy of the Albani Antinous relief. Archaeological simulations have not been limited to stable objects like statues, buildings, and cities. Dynamic processes have also been physically modeled. In fact, I know of 2 physical simulations of the Buchner thesis. In the interest of time, I will show you only one, the simulation that Buchner himself helped to create. In 1995, Edmund Buchner himself appeared on a German TV program for children called Die Maus. I knew you would laugh. Does that still exist? Are they still? Yes, okay. Well, in 1995, they had a program called The Biggest Sundial in World History, featuring Professor Buchner. And you can see him there with the host walking down the Via di Campo Marzio in Rome. And let me show you the clip that shows this physical dynamic simulation.
Und wenn der Schatten dann hierhin gewandert ist, dann weiß man, heute ist der 23. September und die 2. Stunde. Und dann wandert der Schatten den ganzen Tag lang weiter, immer entlang an dieser Linie. Und je nachdem, auf welche andere Linie der Schatten trifft, weiß man genau, wie spät es ist. Jetzt ist es zum Beispiel 23. September, 5. Stunde gleich 11 Uhr. Und das ist genau die Mittagszeit, 6. Stunde 12 Uhr. Und an diesem 23. September, dem Geburtstag des Kaisers Augustus, kommt noch eine Besonderheit hinzu. Da wandert der Schatten am späten Nachmittag genau mitten in die Ara Pacis hinein. Und das hatte symbolische Bedeutung und sollte allen Leuten zeigen, dieser Kaiser hat endlich Frieden gemacht und sogar die Sonne bedankt sich an seinem Geburtstag dafür. Die Sonnenuhr des Augustus war die größte Uhr, die jemals gebaut wurde. Wie riesig die war, sieht man, wenn man einen Menschen im gleichen Maßstab daneben stellt.
To its credit, the Mouse's model puts the studio light simulating the sun onto a metal track, which I would guess was based on real research into the apparent path of the sun through the sky on the day in question, September 23rd of 9 BCE. But as we will see, the Mouse model fails as an exploratory tool, a tool to bring forth new information, because of several instructive shortcomings. First, it claims to prove Buchner's theory by showing that the shadow of the Gnomon sphere atop the obelisk touched the upper stairs of the Ara Pacis. But this is not what Professor Buchner led us to expect, which was the shadow would go genau mitten in die Ara Pacis hinein, not ghost, but host, Armin Maywald put it. That is right into the middle of the Ara Pacis. But there's a more important problem typical of physical models. They may scale when it comes to aesthetics, but not to physics. In this case, we know that the shadow of an object, the probable size of that sphere on top of the obelisk, has no salience. It's not visible at a distance of 90 meters, separating the obelisk from the altar. At this point, I should note that despite all of the criticism of Buchner's work that I'm bringing forward this evening, I would be the first to express my admiration for his courage in publishing his theory before he did any field work, for the seductive ingenuity of the theory, for his energy and resourcefulness in studying the area of his hypothesized monumental sundial, and last, and certainly not least, the fact that he gave his papers, his archive, to the German Archaeological Institute in Munich, which has asked me to publish it. So I have benefited greatly from the material that is in the Buchner archive, and I'm certainly grateful to him for that. Finally, Buchner's theory brought front and center to studies of the culture of the Augustan age a new question, the one we are now considering about the nature of the symbolic relationship between the Ara Pacis and the obelisk. Without Professor Buchner's insights, it certainly would never have occurred to me to work on this problem. The big advantage that our group had over Professor Buchner and his team is that we had the use of an interactive computer simulation. Professor Buchner, when he wanted to determine where that shadow was going, cast by the obelisk toward the Areopagus, had to make the calculations by hand. And it takes a lot of time, and it's very complicated, and it's easy to make a mistake. Our computer simulation has the calculations built in, and there are millions of them, 1.5 trillion of them, in the zone in question that you conceivably could want to generate in the 40-year period in which the timekeeping device we know functioned. Over a trillion. We can get anyone we want instantaneously with no human input at all. So that was a great advantage. And so we created the simulation to give us the chance to go back in time, in effect, to do virtual time travel and to do empirical studies of this visual relationship, and just to see what we could see with no preconceived notion of what it was that we might find. So we call our simulation the Virtual Meridian of Augustus. An earlier version of it was published a few years ago in that journal that was mentioned in the introduction, Studies in Digital Heritage. Now there's a new version that's not yet published, so you're seeing it for the first time tonight, and I prepared a little quick introduction to it.
Welcome to the Virtual Meridian of Augustus, a computer application for web browsers and personal computers developed by the Virtual World Heritage Laboratory of Indiana University and the Institute for Intermedia Arts of Ball State University. As you can see, the user interface of the Virtual Meridian allows us to do many things. In this introduction, I will concentrate on just the basics. First, let us take a look around to see the features of the virtual world in which we find ourselves. In front of us is the Montecitorio obelisk in its original location in ancient Rome. If we turn around, we can see the Areopagus, and note that you've seen the Mausoleum of Augustus off in the distance and also before the Pantheon. We can not only turn 360 degrees, we can also roam freely through this part of the northern campus marshes. Now I'm moving left, and now I'm moving back to the right. We can not only explore views of the monuments on the ground, but we can also observe the sun in the sky overhead. So let's turn around again and look up in the sky to do that. You can see the sun over here to the right of the obelisk. If I change the hour by using the slider, you'll see the sun as I go back in time rise higher in the sky toward noon. And if I go in the other direction on the slider, we're going downward toward sunset. The movements of the sun are accurate on a minute-by-minute basis over the 49-year period from 9 BC to 40 CE. Just as the built monuments are accurately situated on the ground based on archaeological survey, the positions of the sun are also very accurate because they are generated by NASA's Horizon Systems database. So one basic function of the virtual meridian is to allow us to quickly discover alignments between the sun, obelisk, and altar. Another function is to help us to understand the operation of the timekeeping device of which the obelisk and meridian are a part. Very often for doing this, we want to have a top-down view, and the virtual meridian makes it easy to have one, as you now see. Once we are situated in the air, we can turn on various layers that may help us with our investigations. For example, we can turn on a layer that superimposes Edmund Buchner's horizontal sundial over the area. We can understand the relationship of the ancient and modern features by turning on the modern cadaster. If we turn on the meridian line and then the meridian fragment, we can see where the section discovered by Professor Buchner is located. We can zoom in on it to understand how the shadow of the Gnomon globe atop the obelisk cast its shadow onto the various crosshatches in order to reveal the noon hour on a certain day. We can also see how the meridian may have been intended to provide the Romans with an easy way to track the progression of the leap years. We see this when we change the year while keeping the date and time the same. For example, now we are looking at May 3rd of 9 BCE, and the time is 11:04 a.m. Universal Time, which is 12:04 p.m. in Rome. Let's see what happens when we go from the current year of 9 BCE to 8. Note that that shadow moved to the south. Now let's try 7 BCE. The shadow starts to move its way back to where it started from. And now 6. It's moved back even more. And 5, the next leap year, it is returned to where it started. Well, there are many more things that we can do with the virtual meridian, but this should be sufficient as an introduction. You can access the virtual meridian at no cost at the URL on the screen.
Here is that URL again. Now let's see what new facts the virtual meridian has brought to light. First, it is important to understand that the tool reflects our findings about the phasing and design of the monument. There was just one phase and only a meridian. So we dispensed with Professor Buchner's theory that in the Flavian period, the entire timekeeping device was restored at a higher level, 4 meters to the east, that is closer to the hour Pacis. Rather, our simulation reflects the facts that Professor Buchner actually found, a pavement at 10.8 meters above sea level with a meridian line that was never moved or changed. We made the virtual meridian as wide as the data from our GPR transect L3 suggested it was, 14 or 15 meters. The first thing we used the simulation to do was to test the validity of Professor Buchner's theory that the shadow of the obelisk extended into the middle of the hour Pacis on Augustus's birthday. Of course, now that the obelisk is 4 meters farther away to the west than it was even in the physical model we saw in the mouse, the shadow is unlikely to have reached that far. And indeed, as you see in this short video, the shadow reached only the bottom of the staircase up to the western entrance of the hour Pacis. And now we're changing the date back to the 23rd, Augustus's birthday. And there's where the shadow gets closest to the hour Pacis. It just about touches the bottom step of the western staircase up to the altar, but it's very far from going into the middle of the altar. Next, we wondered if what Professor Buchner thought happened on Augustus's birthday happened on other days of the year. For Buchner, someone trying to answer this question before we created our simulation, this would have taken a great deal of time to calculate, so it's not surprising that nobody ever did. But once we had the simulation, it took only a few minutes to determine that the shadow went into the middle of the hour Pacis on these 48 days of the year. But beyond the critical testing of Buchner's theory, we used the simulation to undertake new empirical research, making observations and explorations around the monuments with no idée fixe in mind, except perhaps the idée fixe we inherited from Professor Buchner, that the sun ought to be playing some role in tying together the obelisk with the altar. Roaming around the virtual Campus Martius and moving the hour, date, and year dials for several years in the period 2011 to 2015, here are the new facts that gradually emerged. The key fact was that what caught Buchner's attention about the obelisk's shadow was caused by something even more fundamental and, for me at least, attention-grabbing. The shadow of the obelisk can only be projected toward the hour Pacis because the sun is on axis with the top of the obelisk, giving you the awesome view, or in terms of the ancient sun cult, the hierophany, seen in the slide on the screen. Thinking about it some more, we wondered if the even more impressive sight ever occurred in which the solar disk was seen touching the top of the obelisk while on axis with the obelisk and the altar. We were quickly able to move the dials on the virtual meridian to find one such alignment, as you can see in this slide. Having found this effect, which, since we are looking toward the west, occurs in the late afternoon, we wondered whether there was something similar in the morning. a hierophany in which the solar disk was seen seemingly rising on axis behind or out of even, the Pacis. As you see in this slide, we quickly found this awesome effect as well. In a few minutes, I will discuss the interpretive reasons why looking for such effects is not arbitrary but justified by ancient evidence and concepts. Of course, this doesn't mean that the new interpretation I am about to propose to you is correct, but it is, at least I hope you will agree, plausible and worth considering. Specifically, we found that for analytical purposes, you can divide the zone of interest, the area of interest, into 4 zones. Zone 1 runs from several hundred meters west of the obelisk to the base of the obelisk. It is one of 2 zones where we have intervisibility, that is, where you can see both the obelisk and the Pacis at the same time. In Zone 1, we found 95 days with solar alignments tying together the obelisk and the Pacis. The dates in the area studied range from May 8th to August 10th and occur in the early morning, not long after sunrise. There you can see one such alignment. Zone 2 runs from the west entrance of the Pacis to a point about 23.5 meters from the obelisk, where the summer solstice is reached. In the video, we are standing just inside the west entrance of the Pacis, looking toward the obelisk 90 meters away to the west. In addition to the solstice, June 24th, there are 2 groups of dates running from March 19th to June 23rd and from June 25th to September 27th in which these solar alignments occur, and you're seeing one such alignment in the video. The solar alignments occur in the mid to late afternoon. Altogether in this zone, we have solar alignments on 189 days of the year. Zone 3 starts at the obelisk and ends at the west entrance to the Pacis. In this zone, which also exemplifies interpositionality, you're in between the 2 monuments, the observer puts the obelisk to his back and faces the Pacis to the east. We observed 111 dates on which a person standing somewhere along this line and looking east would have seen the sun rise on axis with the Pacis, and you've seen one such example in the video. Finally, Zone 4 is like Zone 1, characterized by intervisibility. It runs from several hundred meters east of the Pacis to about 14 meters east of the east entrance to the Pacis. In the video, we are about 60 meters to the east of the Pacis on the eastern edge of the Via Flaminia. In the area that we studied, alignments were found in the mid to late afternoon for the period from February 28th to March 13th and from October 3rd to October 17th. Altogether, there are 32 days on which solar alignments occur in Zone 4. To summarize our findings in all 4 zones, the dates when solar alignments were found range from February 28th to October 17th. There were alignments a minimum of 224 days of the year along the line connecting the Pacis and the Montecitorio obelisk. If we add the 48 dates of shadow alignment, we get some 239 days in the period February 25th to October 21st each year, when there was at least one solar or shadow alignment each year, and sometimes there were both. Interestingly, the one date with both a solar and shadow alignment seen while the ancient observer had to stand in the exact same spot occurred on September 23rd, Augustus's birthday. As you may recall, this is the date that Buchner thought was the key to everything. And the spot where you had to stand is also not just anywhere along that axial line, but is a strongly marked spot. It was located right at the foot of the western staircase into the Pacis. This short video shows you what it might have looked like to stand here on the late afternoon of September 23rd in the year 9 BCE. So here we are facing east at the foot of the west staircase. You can see the top of the obelisk just hitting the staircase. Now, if we turn around and look at the obelisk right from the same spot, we have, bingo, that solar alignment. So it is possible that Augustus did intend to mark his birthday as a special day among the 239 days when an alignment, whether solar or shadow, occurred. Be that as it may, there is no doubt but that Augustus also meant to, and perhaps primarily meant to, honor the sun god. This is clear from the still extant inscription on the base of the obelisk, dedicating it to Sol, the Roman sun god. If we would like to update and recuperate Professor Buchner's thesis and speak of the role of Augustus in all this, we may say that Augustus made his birthday the moment in time celebrated forever after on the religious calendar as a holiday, as we know it was, in which the sun god intersects with and is incarnated in humanity. Augustus, like the Egyptian pharaoh, and he was the first Roman to be Egyptian pharaoh, is the son of the sun god and is also the sun god's incarnation on earth. In this connection, it is relevant to recall that in Augustan propaganda, the emperor was presented as the son of Apollo, a god with strong solar association in Greece and Rome. Sometimes, as in the case of this gem in Florence, he was even assimilated to his tutelary divinity. The concept of Augustus's special relationship with Apollo had a strong Egyptian resonance, since the pharaoh was always the Sa-Re, or the son of the sun god Re. Even on the Montecitorio obelisk at the very top, Psamtik II, the pharaoh who made that obelisk originally in the 580s BCE, is addressed as Sa-Re. Here we should recall that Augustus was not only the first Roman emperor, but the first Roman to be the pharaoh of Egypt. To conclude, I believe that beyond their archaeoastronomical applications, an approach like the one I've just been presenting will do two important things in terms of the development of the humanities. For the first time, it will make historical studies empirical, or what I like to call sympirical. Sympiricism is a word I coined combining empiricism and simulation. Before the digital revolution, we never could travel back to the past to make observations and to run experiments. Now, thanks to sympiricism, we can. Secondly, I wish to stress that by exemplifying sympiricism in today's lecture with a case study involving archaeoastronomy, I do not wish to suggest that sympiricism is limited to this one rather restricted area of humanistic research. Rather, as we apply sympirical methods, we are bound to make many more discoveries of unsuspected ways in which monuments, buildings, and settlements functioned and yielded meaning in relation to, yes, the heavens above, but also to human beings on the ground and to the monuments on the ground as well. Since the vitality of a discipline is largely a function of how productive it is in bringing to light what was previously unknown, virtual archaeology is, I think it's safe to say, one way in which the new digital humanities can help to keep the old humanities alive and well into the 21st century. To be sure, in doing so, we will take advantage of advanced technology, scientific knowledge, and the new methodology of sympiricism. However, I hope I have shown this evening why the use of a scientific and technological approach need not in any way compromise the central task of the humanities, which is not to measure, to weigh, and to determine the physical composition of things, but to tell us why things should matter to us in purely human terms. Thank you very much.